Vielen Dank, Marjan. Good afternoon, ladies and gentlemen. My name is Arik Ulch, Business Development Manager at MKS Instruments Germany, and I would like to welcome you to our first Tech Talk presented by an external company. Mr. Rainer Pokorny, CEO and CTO of IAG-nG GmbH, is going to present their first FTIR-based portable emission monitoring system, which has been released recently. The IAG OFS is actually the first OBD FTIR system that is sufficient light and compact enough to be mounted on a passenger car's tow ball, and which can also withstand very rough road environments. It is equipped with the latest low-pressure calibrations and based on the MKS 2030 FTIR spectrometer. The OFS is able to simultaneously detect a large variety of different species, especially gases like ammonia, formaldehyde, N2O, NOx, water, and different hydrocarbons, as well as sulfurous components. Before we start the webinar, I would need to inform our participants that this session will be recorded and published on YouTube for those who cannot join today. In addition, we would also like to mention that during the presentation, all participants will be muted, so the microphones can be unmuted in the Q&A session later on. The questions can be then raised at the end of the talk, either by using the chat function or the audio channel. If you have any technical issues in the meantime, then please use the chat at the event platform for further support. Please let me welcome now Mr. Rainer Pokorny. So Rainer, the floor is yours.
Thank you, Arik. So hello and welcome to this MKS Tech Talk webinar about the IAG-nG FTIR PEMS system. My name is Rainer Pokorny. As Arik mentioned just before, I'm responsible for technical development at IAG-nG. And together with my brother Dieter, I'm running this company since about 20 years. I want to thank MKS for inviting us to this webinar. This is a great pleasure for us to be allowed to present on this platform. So let me explain the plan for the next hours. For the next hour, more or less. First, I will explain who IAG-nG is and our approach to developing an PEMS FTIR system and how we put this into practice. And then a few words about the specifications and the use of the system. My colleague, Mr. Mock, is sitting here next to me, and he will have a look on the chat function and can answer questions during my presentation. And he will also assist me to answer software questions, for example, at the end of the presentation when we have time for Q&A. So let's start with the presentation. First, the presentation outline. First, I will tell you a few things about our company, IAG-nG. Then I will give an overview about the development, plus system and FTIR specifications. Then some data we are allowed to show. It's always a little bit hard to get data we can show in a presentation. Then a few comments on regulations and some thoughts about safety as well. So the company ATEC was founded in 2002 by my brother and me, and we started building modules for the exhaust gas analysis. Our first FTIR system was built in 2007, and since that we have delivered about 170 FTIR systems to countries all over the world. All of those systems are equipped with MKS 2030 spectrometers. As far as we can say, we have a FTIR market share of about 50% in Europe, in the automotive development market. All those FTIR systems are for the gas analysis of combustion engines. These systems allowed us a relative constant growth of about 20% per year over the last 15 years. And we are spending about 10% of the turnover for development. The first FTIR sketches, the first sketches for FTIR PEMS system are almost 10 years old. But technology did not allow to create a system that would fulfill our internal requirements before that. In the meantime, we developed the NH3 laser PEMS system, which served as a development platform to gather some experience with portable emission testing. But I don't know when this was exactly, a while ago, when the first REF-G prototype, the last generation of the 2030 FTIR, the so-called REF-G, was in our lab, and we opened the hood of it. It was instantly clear that now it's possible to develop an PEMS FTIR system. Because MKS has really done a great job in making the internals so much lighter and more compact, that in addition with a low pressure calibration, which I will explain a little bit later, it was now possible to create a PEMS FTIR system as we thought it might be necessary. That means it should be a system that can be mounted off a tow bar of a passenger car, or in some cases on the passenger seat of a car that doesn't come with a tow bar. After some delay due to COVID-19, the OFS has finally been released in April 2021. So what has been the development task for this so-called OFS system? We were thinking about the weight of maximum 50 kilograms to allow handling by 2 persons without using a crane. We aimed at a device volume not larger than the MKS housing of the 2030. We wanted to create a shock absorption that allows the use of the system even for light off-road use. It was very important to set up a system that only needs the least possible consumables. It had to have good access to all relevant components for quick maintenance. It must be easy to install on tow bars, and it should also be ready for test cell operation. I will explain that a little bit later in more detail. So what weight concerns, lightweight construction is not a common task in building analysis equipment. But since I'm building racing motorcycles in my private life, this wasn't something very new for me. But still, it was not a simple task to create an FTIR system with all the internals with a weight of less than 50 kilograms. Actually, it wasn't really possible to build the entire system with 50 kilograms. So we have 50 kilograms for the FTIR system on the tow bar or in the trunk. And we have another battery pack that we need for power supply of the systems that has another 25 kilograms. I have to mention this. Yeah. Putting all the gas handling components as well as a PLC and an industrial PC and a lot of other stuff in the volume of a MKS 2030 housing turned to be a really hard task. So in the end, we had to grow the volume by about 15% over the MKS housing. After some additional development work, it was possible to create a shock absorption, which allows testing on unpaved roads without losing any data points. So we have been a lot of road testing and bed road testing and unpaved road testing, just to improve the suspension of the internal parts. But we have to do a lot more testing with this, for this. And all this wouldn't have been possible without the MKS components being very rugged anyway. So an FTIR, an MKS 2030 FTIR, sorry, as it is, also can handle a lot of vibration. To make the handling of the OFS as simple as possible, we tried to use only the least necessary consumables during road testing. So it's still an FTIR, and since we want to measure NH3, it has to be filled with liquid nitrogen for the test rides, and it still needs gas nitrogen for gas cell purging, but only during warm-up in the lab, and it doesn't need anything else than electricity during road testing. Another major development task was the serviceability of the system. To create a device with the smallest possible volume, it was necessary to pack the internals as compact as possible. Nevertheless, all maintenance relevant parts are easily accessible to allow a very short maintenance time of about 1 to 2 hours. Additionally, we created a few easy removable sub-assemblies to allow good access to all other parts as well, even though those parts that usually do not need access, because experience showed that the best hidden parts are always the parts that break down first for some strange reason we don't know. For the tow ball mounting system, we decided to use a quick release system that consists of 2 parts. The first part is the tow ball rack itself, which has a weight of about 12 kilograms and can therefore be mounted and adjusted on the tow ball by only 1 person. Part 2 is a frame that is bolted to the underside of the OFS. This frame has extra handles and eye bolts for crane handling if necessary. So frame and OFS, which are bolted together, can be mounted to the tow ball rack by a quick release system. And this frame also incorporates a license plate holder with battery powered lighting and a EFM mounting bracket. Oh, sorry. So the system also has a few options, as you can see in the picture on the right. Here on the right top, you see an ISOFIX base plate, which can be mounted on rear seats of passenger cars. And on the picture below, you see this explosion view of the OFS with a rain cover on the right side, the subframe with the license plate holder with lighting. The lighting is powered from the OFS from the battery system. And at the bottom of the system, EFM can be mounted, so we have an EFM interface ready as well. Because we wanted to have the system ready for test cell operation as well, we decided to run the system on 115 for the US market or 230 volt for Europe, which makes the handling on a test bench a lot easier because you can just connect it to grid power and it would run like a standard, more or less like a standard FTIR system, of course, with a little bit reduced functions due to size and weight issues. But in the end effect, it has got the same measurement physics, so it will show the same accuracy, for example. And Yeah. Another reason for the high voltage supply was since we have the battery pack in the trunk of the car, we have to run power cables through the trunk lead to the OFS system. And 230 volt just allow thinner cables than if it was 12 or 24 volts, for example. So it's not only a PEMS system, it can also be used stationary. Yeah, we have 3 different battery packs available, one with 100, 160 and 200 amp hours. I will explain this in detail a little bit later. So on the next slide, we have a gas flow diagram, which shows the internal construction. I mean, it doesn't show all details here, but a general overview. The system is a vacuum system, which means we have a sample gas pump downstream of the FTIR. And in the FTIR, we have a gas cell pressure of 800 millibars, which means under pressure. So, but first things first, point 1 here on the left side would be the gas inlet. This is normally a heated line with about with 1.5 meters, which is connected to the OFS system via a Winkler quick connect system, which turned out to be very practical. Number 2 here, this area is the heated filter and valve block. This is where the gas is entering the OFS. At first, we have an inlet filter, which is the standard IAG filter element, which we are using since many years because we have tested a lot of different filters for NH3 analysis, and this one turned out to be the best performing filter we have seen. Next is number 4. This is a inlet gas pressure regulator, which allows gas inlet pressures up to 6 bars, which would maybe occur on if the system is used on a test cell with PEMS uses normally not. But actually, we are using this pressure regulator as an inlet valve as well, so it has got a double function, and therefore it was no extra effort to put in that. After this, we have a car gas valve, where we can switch car gas to the calibration gas to the analyzer. Actually, we have 3 possibilities to bring calibration gas to the analyzer. One is this calibration gas inlet inside the system. Another possibility would be to feed calibration gas to the sampling point, which is possible because this system also has a calibration gas outlet. So you can connect calibration gas to the OFS and send it out to the sample point or to an external valve. I will explain this later a little bit more in detail. What we have here on the output of the inlet filter block is a flow control valve and electronic control via the device software. This was possible because it is necessary during on-road testing on different altitudes to maintain a constant flow through the system, because the dynamics would change otherwise. So with this system, it's possible to set the software flow, for example, to 6 liters, start at sea level, and make an on-road test up to 1,800 meters as we tested it. And if the flow of 6 liters is adjusted in the software, it will stay at 6 liters during the whole test, as well as the pressure inside the FTIR will also maintain constant at 800 millibars. So actually, this was a very important development goal for us to achieve this kind of action. So here, number 5, we have the FTIR. We have nitrogen connection for the device purging. Then on the top we have a liquid nitrogen orifice. In this case, we made this a closed system, so when there is liquid nitrogen filling, you have to remove a cover on the top, fill nitrogen and close it again, because otherwise the liquid nitrogen evaporating would go into the passenger cabin of a car, test it, which is not a good idea actually. So in this case, we have an exhaust line feeding the evaporating nitrogen gas to the exhaust of the system. Later downstream, we have a flow measurement and a condensate tank with a level switch, which shows when the condensate is full. After that, we have the downstream sample gas pump and an outlet with an outlet valve for safety reasons. I will show that later. The entire gas path of the OFS, including the FTIR gas cell and the filter chamber, is a little bit less than 100 cubic centimeters. This was a side effect of the very compact design of the system, and it turned out that it's very responsive due to this very small internal volume. So next, I show you a little bit about the system layout. Here is a view of the front panel. Basically, all connections of the system are on the front panel, except for the liquid nitrogen refill, which is on the top of the system. When it's mounted on the tow bar, it can be mounted with the operation front oriented to the right or to the left side of the car, because the base plate is symmetric. The dimensions of this OFS are 600 by 500 by 400 millimeters. The weight I mentioned already is a little less than 50 kilograms. Gas cell pressure is 800 millibars. That means we are running specially developed low pressure method. The power consumption of the system is about 250 watts. Interestingly, it turned out that the OFS itself doesn't consume very much electric energy. The greatest consumption comes from the heated lines. And actually, this is a reason why we have three different battery packs, because in the basic configuration with 1.5 meters of heated line, a 100 amp hour battery pack would be good for about 3 hours of testing. But on some cars where there is no tow balls, for example, if sports cars, 2-seaters or something, where the OFS has to be mounted on the passenger seat, it's necessary to route a very long heated line with, say, 5 or 6 meters to the exhaust system. And this heated line, it takes so much electric energy that we had to create a greater battery pack as well with 200 ampere hours, which is good for, I think, 4 or 5 hours at least, or 7 hours with a short heated line. Then let me go through the connections. At the top left corner, we have a network connector, which is for remote desktop operation. Beside that, there's a USB port, which is normally used for GPS mouse. And on test cell applications, we can use an Ethernet connector and run the AK communications over this interface. Right of this, there's a power switch, of course. Then we have a connector for a license plate light, because it's not allowed mostly to power the license plate light from the vehicle's electrical system. That's why we are running this from our battery pack. We have also EFM interface as standard. This is an interface for an AVL EFM, because this is the widest used EFM. So we have two connectors, one is for the power supply and one is for the network connections. Then we have two heated line connectors with maximum 5 amperes. One is for the heated line, and the second one would be for additional filter or something. So normally you won't use it, but there is two heated line connectors. Then we have a power supply connector, of course. Then we have another connector which is for an external valve, which allows span gas to be switched on the beginning of the heated line. I don't have a picture here, but we have a small box with a T intersection that can be mounted to the gas inlet of the heated line, and which allows to switch calibration gas on overflow to the gas inlet of the system, which comes from the system and can be switched from there. Then we have a filter element here, which can be changed from the front panel. So it's the filter element I mentioned before in the gas stream. Then we have a heated line connection, as mentioned before, with a Winkler Quick Connect pin. Then we have one span gas connection, we have one zero gas connection, we have one span gas outlet, as I mentioned before, for connection to the external valve. And then we have an exhaust connection. All of these connections have check valves built in. So, for example, if there is no exhaust connected, the system would switch off because there is wouldn't be a sample gas flow or a span gas flow, and the system will realize this and will switch off and not measure. So next I would tell you a little bit about the software and operation. The software is developed and supported by IAG, so it's our own software. Of course, there is the MKS MG 2000 software in the background, but normally you wouldn't use it. Operation can be done via remote desktop. The operation system is Windows 10. We have different test routines and reports according to EPA 1065, which is in the system. The system itself is PREN 17507 compliant. Almost, if I have to confess, because we have a little few more tests to be done, like tilting tests and that. But actually, we are pretty sure that also this will not be a problem. The operation software also shows measuring values and relevant variables. So the system is self-checking, and if there's something wrong, there will be an alarm, of course. We have a campus interface, a sub-D interface. Yeah, all the connections I mentioned before on the front panel, actually. Yeah. The operation software is based on LabVIEW and is pre-installed on an IPC, which is inside the OFS, so the OFS is really self-containing. And of course, it's important variables like system pressure and flow is automatically monitored and regulated as well. So now a few details about the FTIR. The system is based on the model 2030 REF-G. It's got a 70 cubic centimeter stainless steel gas cell. It's got 5 Hertz analysis frequency. It's got an optical path length of 5.11 meters, which is all standard, as well as the spectral range from 500 to 6000. Spectral resolution of half a wavelength, also standard. We have gold-plated mirrors with magnesium fluoride coating, and we have zinc selenide windows. and a 250 milliliter liquid nitrogen reservoir, which is good for, depending on the vibrations, but at least, let's say, 6 to 8 hours normally. To mention the improvements of the REF-G FTIR in comparison to the REF-D, which was the system we have been using before this. What's really new is a user replaceable laser, which is a good thing because it's mounted in a fixture which can just be unscrewed from the FTIR and changed in a very short time without additional adjustment work. We have now temperature controllers integrated on electronic boards. I mean, the major thing or the major changes to the REF-G was the electronics. So the power supply is electronic. Before there have been a lot of different electronic boards. Now it's only 2 electronic boards left. So actually there is a lot of empty space inside this REF-G system, which makes everything easier because a lot of testing can be done via the software. Yeah, a lot of improvements there. Also, the airflow is improved, which is also an interesting thing because the thermal management is a little bit better. And another nice thing is a fanless IR source. I won't explain that in detail, but it's a nice thing to have. So a few words to the detection limits and measurement ranges. This is just a few components you would normally be interested in when measuring with an FTIR. So in the last, I don't know, more than 10 years, FTIRs have mainly used for NH3 detection, sometimes for formaldehyde detection as well. But mostly for NH3. So in the last 2 or 3 years, or maybe a little bit more, the FTIR became more and more, or was used more and more for not only development, for other gases as well. Let's say it that way. Since we have developed 800 millibars with really a lot of help from MKS as well, as a major German car manufacturer, we did a lot of extension on the method development as well. So NH3 range is a little bit higher than it was at the beginning, and we did a little bit of adjustment on N2O, SO2, ethylene, acetylene, acetaldehyde. So there was and is always a little bit of progress concerning method development. So the measurement specifications, these are the specifications that are required by the EPA 1065. So there the accuracy has to be smaller than 2% of the reference value. The repeatability has to be less than 1% of the reference value. The noise must be less than 1% of the instrument range. The slope has to be between 0.99 and 1.10. The drift has to be lower than 2% of the instrument range, which it is because the drift on an FTIR system is almost 0. We need a spectral resolution of 0.5 centimeters, which is necessary for the detection for this accuracy that is required. And the sample temperature is 191 degrees. So it's in the old system. So the heated line is 191 and the heated filter block is 191, as well as the FTIR gas cell. And Just to mention, of course, all the gas contacted surfaces are stainless steel or PTFE. So then a little bit more info for on-road application. The ambient temperature can be from -15 degrees up to +35 degrees, which should be sufficient for normal PEMS testing. We have tested our system from altitudes from sea level to 1,800 meters. And we had one test in a head chamber, or where we made altitude simulation up to 3,000 meters, and we have still been more or less within range. If somebody requires 3,000 meters altitude, which might be possible, we would have to make a few changes to the method, but actually it wouldn't be a big thing to make this extension. So we are confident that we can do this. I mentioned before the sample gas pressure should be about, or the inlet pressure should be about 800 millibar to 6 bar. Actually, yeah, it can be maybe a little bit lower than 800 millibar, but normally it won't be. The protection class is IP53. This is with the rain cover mounted that I've been shown on the picture at the beginning. Actual acceleration force is up to 6 G. We have done a lot of test rides on our own vehicles where we have put acceleration sensors on the system. We have been measuring up to 6 G without any data point losses. So we have seen if there is very strong vibration, it does have an impact on this measurement signal. But we are still investigating, because actually we see an influence on the pressure of the gas cell. So it's not the FTIR that has some interaction with vibrations. It's more or less our mechanics, and there's probably some room for improvements. This is something we are doing in our labs at present. The power consumption is about 250 watts. I mentioned this before, without heated hoses. So we did a lot of testing, and there has been really a lot of evaluations with potential customers. So we have, at the moment, we have 3 demo systems which are in use since beginning of this year. But most of the data we are not allowed to share. So luckily we got this data from KIT in Germany, where we can really show that we have GPS data from a test ride, which is little less than 82 kilometers with a duration of 105 minutes. And you see this is a standard RT cycle performed with our PEMS FTIR system, which it did without any troubles. What we see here is a comparison of some measurement data. The green graph is our OFS system, and the blue graph is a conventional PEMS system. The correlation is very good, we would say. There is a difference in the signal, because I mentioned before, we have such a small internal volume, and we have a 5 Hertz sampling speed, that the peaks are sharper, of course, but especially on the right graph, you can see that the correlation is very good. So we don't see a lot of problems here. There will be more testing, and we already have more data. and this still looks quite promising, we have to say. Yeah, then a few words to the regulations. What we have at the moment is, or since a while, are the requirements from the EPA 1065. We have a lot of experience with our standard FTIR systems. And basically, it's more or less the same operation software with this almost the same functions. So we have integrated these EPA checks, ARN, HT interference, leak check, response time, linear verification, and we can generate protocols, PDF protocols in our software. Another standard we have is the PREN 7507. So the measurement requirements are almost equal to the EPA 1065. And there is some additional mechanical tests mentioned before. There's some tilt testing and vibration testing. We are in the progress of doing this at the moment. And then we have Euro 7 expectations. Nobody really knows at the moment what will come, but there is some rumors, and it looks like we would say hopefully the FTIR might become certified for all components, which of course would be very interesting for us. There are some additional limited components in discussions, like NH3 since a long time, N2O and Formaldehyde. And probably there will be a wider focus on RDE testing. So then a few words on safety. Our system is TÜV tested, so we have been on the test track with the system. That means that the entire system, including the EFM interface and the rain cover, is road legal in the EU. So there is no restrictions for road use, for example. No speed limits or something. So it can normally be used. I think it says 160 kilometers per hour in the testing protocol. Then a few other safety features are, as I mentioned before, we have check valves on all the gas connections, as well as on the inlets and the outlets. So no hazardous gas can escape from the system or can protrude in the passenger compartment of a car. And we have a sample gas flow monitoring. So that means if there is no sample gas flow, we see that, and we see that there's something wrong, and the device will stop measuring and will purge the gas cell with ambient air, probably. And as I mentioned before, we have the liquid nitrogen aspiration. What you see here on this picture is the open cover on the top of the system. And there's this blue hose in the corner, which leads to the exhaust system. So yes, there's something I forgot somewhere in between. So I will go back to maybe to that one. What I also wanted to explain is how is the operation of the system. So for operation, you need, let's say on a towball, for example, you need the OFS system. If there's bad weather, you would need a rain cover as well. You would need the subframe, and you would need the towball mount, and eventually the EFM interface, as well as a heated line. Setup would be like this. Normally, you would set up the OFS on a lab. That means the FTIR, the OFS is normally put on a card. Next to it would be the power supply module, and then the OFS can be connected to the power supply module and can be fired up. During warm-up, it would normally you would connect to the power module to grid power, because the power module also has a battery charger inside, so it can charge the battery and power the OFS at the same time. So during warm-up, you wouldn't use battery power, you would just need grid power. And if the system is then ready for operation, you just have to disconnect the power supply module from grid power, and the OFS would run in connection with the power supply module. During warm-up, it's necessary to connect the system to nitrogen gas, because then the gas cell would be purged, as well as the
detector box and the optic box.
Yeah, the detector and the optics box of the FTIR.
Calibration.
When the system is warmed up, which normally you would let it run for a few hours to really warm up, you would make a background and then eventually span gas checks. And when all this is ready, the system is ready to be mounted on the toe ball of the car. Normally, the FTIR would be mounted to the subframe with the license plate holder before powering up. And now the car would be ready for the toe ball rack. So the toe ball rack is very light. You can approach the car and mount the toe ball rack to the car. And since this is a very low profile, the trunk can still be opened. And the next thing would be to bring the OFS with the power module to the car, put the power module into the trunk of the car, make a connection to the car's computer, and connect the heated line to the EFM or to some sampling point. Then the OFS with the subframe can be mounted on the toe ball rack with a quick release system. And then basically the system is ready to go. Not to forget to fill liquid nitrogen at some point. So we have reached the end of the presentation, and now we would be ready to answer your questions.
Yeah, Rainer, many thanks for this, I would say, very interesting talk. It actually shows that, I would say, a lot of engineering has been really required to come up with the solution as it is right now. And yeah, I personally like really the idea that the OFS system, which I just learned today, can be used for mobile, but also stationary applications in the test cell. So I think this really provides a lot of flexibility. So which is, I think, quite interesting for quite a lot of customers. As I said, I think we can now start the Q&A session. So everybody, please feel free to raise your questions, as I said before, either using the chat function or the audio channel. If you decide to use the audio channel, please unmute yourself.
There's no questions. It seems
I have a question. Benedict Grob from AIP. Hi,
okay.
Everybody. One question about the detection limit of the FTIR. You said that you can also imagine to use this system for Euro 7. But if I see on your slide, no, it was the slide where you showed the detection limits.
Page 8.
Yeah.
Page 8.
Yeah, there you write for NO and NO2, 2 ppm and 1.2 ppm. So if you sum up, yeah, you are maybe around 3 ppm for NOx. You think this is sufficient for PEMS applications? Because yeah, if you see the Euro 6 PEMS, they are maybe around 0.5 ppm right now. And we are now at a limit of around 80 or 60 milligrams per kilometer. It will be going down, nobody knows, to 30, something like this.
Actually, this is a very interesting question because on one hand, we are aware of this and we are trying to improve the calibrations for NOxes. And on the other hand, we are just building up a new system, which is not an OFS system, but a stationary FTIR system, which is called our low NOx system because of future requirements. And there we are just in the process of evaluating other possibilities to bring down the NOx detection limits. It's not really ready, but I can tell you that we are aware of this fact and that we are investigating here and trying to improve. So you are right. At the moment, it's a little bit critical.
Mm-hmm. But you want to apply new methods, or you're using a different spectrometer for achieving this?
Actually, there is no different spectrometer. We can just try to improve the method or the calibration and see if we can get there something. It would probably be possible, but we don't know exactly to which extent we can improve the detection limits. It's not really clear at the moment.
Okay, thank you.
Okay, you're welcome.
So I don't see any questions in the chat. So I don't know, are there any additional questions from the audience? Just don't hesitate. Please feel free to ask.
Or if there's any questions later that might come to your mind, you can still contact us. So, no problem.
Okay, then I have another question. If nobody wants to ask. So the rain cover you're using, with this rain cover you achieved the IP53 or
53, I think, yeah.
Okay, so it's with the rain cover.
Yeah.
And then another question about Euro 7. So if you want to use it for a PEMS, you also need particle number.
Next good question. Thank you. Yeah, another thing we know, and of course we have a lot of requests for particle measurement as well. At the moment, there is only one system available that we can provide additional to our OFS system. For that reason, we are in the process of developing our own PEMS, our own particle system, but this will take us another year or so probably. So we have a system that we can offer at the moment, and we are working on a more compact solution as well. So this the particle measurement and the EFM are the things where we, along with the NOx, are things where we still have to do some work, because probably you also know that the EFM accuracy might eventually not be sufficient for real RDE testing.
Mm-hmm.
But we don't really know at the moment. There is the standard. Everybody is using this type of equipment, but probably also there will come something new in the next, I don't know, in the next years at least.
And will it be CPC based or diffusion charger system?
No, it will be probably CPC based.
Mm-hmm. Okay.
We are not 100% sure, but most likely yes. But unfortunately I'm not the specialist on particle measurement. I have my colleagues working on that. So, but yes, generally said, there is still a lot of development work that has to be done around this FTIR PEMS system. But at the moment, we are really happy that we have been able to develop this system and make the first step in this new direction. And there is a lot of interest in this FTIR system, but of course there will be changes and there will be additional tasks. Mm-hmm. So we do not expect to stop our development process at this point.
Yeah, I mean in the boundaries of Euro 7, they are also not really clear right now. We have to wait a bit more or till next year.
Yeah, as I said, we did the first step, and now we can get some experience. The regulations will become more and more clear in the next month and years probably. So, and we have to adapt to these regulations step by step.
Mm-hmm.
But we already reserved a lot of development budget for this.
Okay, there are just a few minutes left. So are there still any questions? So if not, Rainer, once again, I would like to thank you for sharing all that information with us. It's been a very interesting topic, especially in regards to Euro 7, which has been just discussed, including the increasing demand as we see in mobile emission monitoring systems. As Rainer mentioned before, in case anyone has further questions later on, just feel free to reach out to Rainer or to myself. Yeah, I would like to thank you for joining and wish you all the best. Just stay safe and see you soon.
So thank you for inviting me to this Tech Talk, and thank all the participants for their time and for their interest. I hope it's been an interesting presentation and you have learned something. And yeah, thank you and all the best.
Thank you, Rainer, again.
Thank you.
All the best.
Thank you very much.
Bye-bye.
Bye-bye.
Thank you.
Thank
Bye-bye.
you.
Bye.
Thanks. Bye-bye.
Thank you. Bye.
Thank you. Bye-bye.